Again, zi minus z bar, yi minus y bar. So z is zi minus z bar. Y is y minus y bar. Xi is summation xi is xi minus x bar. Right? Okay. So this can be written as, this we said is equal to yeah, folks? Right? So I have again, assuming no autocorrelation, no heteroscedasticity, this becomes is equal to yeah. Right? Oh, now remember, I have zi xi square. Right? I can now write this as, this is equal to sigma square summation xi square. Okay? Right? So let me divide this by summation xi square. Right, so let me do a little bit of a more important thing. Okay, I can do this. I can write this as sigma square summation. I can divide this by summation xi square. Okay, I can multiply. Yeah, numerator I am divided by summation xi square, multiplied by summation xi square, and the denominator remains summation zi xi the whole square. Right? Simple trick I have done. Right? In the numerator I divided by summation xi square and multiplied by summation xi square. Now guys, do you see what this is? Who can tell me what this is? What is summation zi xi? Covariance between zi. What is summation zi square? What is summation xi square? Variance. So this is variance of x into variance of z upon the covariance xz whole square. But what is that actually? Okay, tell me, what will be the correlation between x and z? Covariance xz, right? Okay, so if I write this here, correlation xz is summation xi zi. Actually, there will be an n here and there will be an n here and n here also, right? Okay, sure? So those n's will cancel, right? So what do you see there? So what will that mean? So I know this is summation zi square. So what I have done is simply divided by summation xi square, summation zi square, right? Actually this will be like this, yeah. Summation zi square, summation zi whole square. If I divide by summation xi square, multiply by summation xi square, so what do you get? You see friends, that this is equal to, this is the variance of beta hat OLS. Isn't what you have 1 upon correlation xz square? Yeah? Do you see that what we have is 1 upon correlation xz square?
Doesn't that have to be the whole square for it to be correlation?
Which one?
The summation zi squared xi squared.
See, summation xi, what is correlation xz? Xi zi upon summation xi square, right? Okay. So, if I square this, the whole square, what will I get? What will I get? Summation xi zi, the whole square, right? Okay, upon summation xi square square, summation zi square square, right? Now what is correlation? The correlation actually is this, no? It is covariance xz upon the standard deviation of x into the standard deviation of z. That is the correlation. If I square this, I get this as 1 upon correlation zx square. Right? So we got an important issue, right? What we got is something very, very interesting. It says that variance of beta hat IV by R square, I mean the correlation between x and z. So what do you think will be the relationship between variance of beta hat OLS and the variance of beta hat IV? Which will be larger? Beta hat IV will be larger because correlation is bound to be between 0 and 1. So that 1 upon R square will be a number 1 upon a number less than 1. So 1 upon R square will be a number greater than 1. So beta hat IV will be larger, variance of beta hat IV will be greater than the variance of beta hat OLS. Right? So this is an important issue that you must remember. If you try to solve a particular problem in econometrics, it gets solved but there is a price that you do. Yeah? So the higher variance is the price that we are paying for being able to solve for beta hat at all. See, when we do the OLS, because x and e were correlated, we could not use the OLS estimate. So beta could not be estimated. So we thought, okay, we will then use an IV estimate. But the basic principle in economics is you can never have a free lunch. When you get something, you have to give up something. There is a trade-off. So the trade-off here is, if I am solving for the variance, if I am solving for, in order to estimate beta without the bias, I am actually allowing for a larger variance of beta hat IV. A larger, greater inaccuracy of beta hat IV. Right? So I have to then take the chance that I might actually be able to estimate beta hat, but I might not be able to take tests of hypothesis. I might not actually be able to take tests of hypothesis properly. My power of the test will go down because the variance of beta hat IV is larger than the variance of beta hat OLS. Right? So if you solve a problem, there is obviously a price to pay for it. Yeah, and the increase in the variance of the beta hat IV is actually the price that you pay. Beta hat OLS into 1 upon, right? Sure? So if x and z are not correlated, what would happen here? If x and z are not correlated, what would be the problem? Variance of beta hat IV will not be defined. Yeah, because you'll actually, the estimator will not exist, no? Because covariance yz upon the covariance xz. If the covariance xz is 0, the estimator doesn't exist. What if x and z are perfectly correlated? Yeah, but then x and z might, if x and z are perfectly correlated, all probability z will also be correlated with E. Yeah? So when you find an estimator, therefore, if you have a worthwhile instrument at all, which is the, if you want to get a beta hat IV, you will most likely you will have to pay the price in terms of having a larger variance of beta hat IV. Okay? Is this clear? How much more time do we have? 40 minutes for 0. Good. So now, so is this idea clear? Beta hat, IV, beta hat. Now, the biggest catch that we have is, I told you how you take a test of hypothesis here, right? But that test of hypothesis, you need to know the variance sigma square of the error term. How will you know the variance sigma square of the error term? You can't know it, no? It's not possible to know, right? Because unless you know it, just like the Z test I told you, you have to know the population variance. The population variance sigma square किसको मालूम है, किसको मालूम नहीं हुआ है? So what do we do? That takes us to one or two other distributions. So now, suppose you have each x1, x2, xn are all coming from a normally distributed population with mean mu, variance sigma square. So you know x1 minus mu by sigma is the standard normal by definition. By definition, right? And so on. Now think of squaring this. Okay, so think of x1 minus mu by sigma square. So you square the first. Then you square the second. And all these are independent of each other. You add it to the first. You square the third. Add it to the sum. Like that, you add these n terms. x1 minus mu upon sigma square, x2 minus. You got a new random variable. This sum will also be a random variable because x1, x2, x3, xn, whichever you are taking from the sample, will differ from sample to sample. So this sum, which we will call will also be a random variable. Will follow probability distribution. The probability distribution which this sum follows is called the chi-square distribution with n degrees of freedom. So when you get the chi-square distribution, if you sum n independent standard normal squares, n independent standard normal squares, then the sum follows the chi-square distribution with n degrees of freedom. So somebody asks you, what is the chi-square distribution? It is sum of the distribution followed by the sum of n independent standard normal squares. The distribution followed by the sum of n independent standard normal squares is the chi-square distribution. Right? Okay. Now I am going to prove to you an important theorem. And if a chi-square is clear, sum of n independent standard normal squares. And why is it said to be with n degrees of freedom? Because you've got n independent sources of variation. you are adding n independent standard normal squares. Each of the square can move independently. So number of independent degrees of source of variation in the summation zi square are actually n. Right? Okay. Now I am going to prove to you a theorem. I am going to prove to you a very important theorem. So if you have suppose you calculate the sample variance from this, which you do by this is how you calculate the sample variance. Does everybody know why when you calculate the sample variance you divide by n minus 1 and not by n? When you calculate the sample variance, you divide by summation xi minus x bar square upon n minus 1, not by n. Why? Because all of you know that the sum of the deviations from the mean will be 0. So if there are 3 observations, say 1, 2, 3. What is the mean of 1, 2, 3? What is the mean of 1, 2, 3? 2. So if the first number is 1, the second number is 2, what shall be the third number? If I tell you that the sum of these 3 numbers is 2, the average of, suppose I tell you that the average of these 3 numbers is 2, right? The first number is 1. I tell you the second number is 2. And I ask you what will the third number be? 3. If I tell you that the second number is 2, the first and the third number is 3, what is the first number? If I tell you the first number is 1, the last number is 3, what will be the middle number? 2. If I tell you the average of 2 numbers is 10 and the first number is 20, what will be the second number? Average of 2 numbers is 10. The first number is 20. What will be the second number? 0. So once I tell you that n independent, I have n observations, and if I tell you that the mean of these n observations is something, then you can only vary n minus 1 observation. The nth observation is fixed. So if I tell you that the sum of 3 numbers is 2, you can choose the first 2 numbers anything that you feel like. Suppose I choose the first number 20. And if I choose the second number 70. So the first number 20 minus 2 is 18. The second number 70 minus 2 is 68. The third number has to be chosen that the sum of all the deviations from the mean has to be 0. So third number has to be such that the deviations from the mean is 18 plus 68, so 86. The third number has to be 84, minus 84. Only then will the average of it 2, right? So you can choose any 2 numbers at random, the third number is fixed. Similarly, if you have n independent observations, and suppose you want to estimate the population variance from that. So each of the deviations from the mean is a bit of information about what is the overall variation in the data. x1 minus x bar is an estimate of what is the x1 minus x bar square, the distance of the first observation from the mean in your sample is some indication of what is the overall variation in the observation in the data from the mean. Similarly, x2 minus x bar square is the distance of the second observation from the mean, is also gives you some information. The question is how many such independent bits of information there are in n data points, not n but n minus 1, because, right? And so if you have to average them out, you average them out not with respect to n but n minus 1. So degrees of freedom here are n minus 1. Therefore, when you form the sample estimate of the variance, you use n minus 1 and not n. Right? Because you actually have only n minus 1 independent bits of information. It's called the degrees of freedom. The degrees of freedom are nothing but the independent sources of variation in a given, independent sources of information in a given data set in order to estimate a specific parameter. Right? Yeah? So the theorem that I am going to prove to you now is, if I take S square and divide it by the population variance sigma square and multiply it with n minus 1. Okay? What I will get follows a chi-square distribution with n minus 1 degrees of freedom. So if I take the sample variance divided by the population variance and multiplied by the degrees of freedom, what I get is chi-square distribution with n minus 1 degrees of freedom. Can you give me a quick intuitive proof of this? And this of course is I was from 1 to 2. Can you give me a quick intuitive proof of this? Okay, what do you think is your first step? Suppose you have to try this out. पहला step क्या करेगा? Summation. So this will be, I will just substitute this formula here. Yeah? क्या कैंसिल आउट होगा अभी? n minus 1 कैंसिल आउट होगा, right? So what is this? Now how many such independent xi minus x bars are there? n minus 1. How many such independent xi minus x bars are there? n minus 1. No? Because the nth xi minus x bar is fixed. So what will be the degree of freedom of this? N minus 1. How many independent standard normal squares are you adding? N minus 1. Because एक x bar है ना, तो एक तो fix हो गया ना x. So n minus 1. So this will follow a chi-square distribution with n minus 1 degree of freedom. As simple as that. Yeah? Because there are n minus 1 independent standard normal squares there, not n. Correct? Because xi minus x bar. ठीक है? x bar minus mu होने से ठीक रहे. Because population है, उसका average है, वो population में 20 observations दिया. First minus the population mean कोई summation that does not have to be 0. Summation xi minus mu doesn't have to be 0. Summation xi minus x bar has to be 0 because x bar is calculated by is summation xi upon n from that sample. So in a particular sample, each value minus the mean of that sample has to be 0. Each value of a sample minus the population mean doesn't have to be 0. Right? Okay. So therefore, summation is a chi-square distribution with n minus 1 degrees of freedom. Okay. This is a useful distribution, but I will come back to it when we require it. Now, suppose I have a summation so I have got some sigma square x. Suppose there is some x, उसका variance sigma square x है popular है, and there is some xi minus x bar, right? Okay. This will be say some chi-square n minus 1 degrees of freedom. Similarly, think of some y. Say I goes from 1 to m and say has a mean sigma square y. So this will be a chi-square m minus 1. Because there are m observations here, So उसका degree of freedom m minus 1 right? Now let me divide it by the degrees of freedom. Let me divide this also by its degrees of freedom and let me form a ratio of the two. So I have first a chi-square n minus 1. I have divided each of them by n minus 1. I have a chi-square n minus 1, each divided by n minus 1. And finally the ratio of the first term. This will also be a random variable. So numerator and denominator are random variable. So it will also follow probability distribution. The probability distribution it follows is called the F distribution with n minus 1 numerator degrees of freedom and m minus 1 denominator degrees of freedom. N minus 1 numerator degree of freedom and m minus 1 denominator degrees of freedom. Okay? Finally, so chi-square हो गया, f हो गया. Chi-square is nothing but the sum of n independent standard normal squares. That is nothing but the ratio of two chi-squares divided by their own degrees of freedom. Now, suppose the final distribution that we are interested in